Hey, P Statistics. Today we're going to get into section 1.3, describing quantitative data with numbers. So these are our summary statistics. So by the end of this section, you should be able to calculate the measures of center, mean, and median, being what we're going to focus on, for a distribution of quantitative data. Calculate and interpret the measures of variability, range, standard deviation, and IQR for a distribution of quantitative data, and explain how outliers and skewness affect the measures of center and variability. And then in the second video, we'll do these other three: identifying outliers using a rule, box plots, and then making and comparing box plots. So let's start with the mean. The mean, you've been doing this for a long time. A lot of people, when they say the average, this is what they mean. They mean mean. We use this symbol X bar, pronounced X bar, to represent the mean from a sample. This is kind of the formula you've always done. You add up all the values and divide by how many there are. You've probably always referred to it that way. You may not have used this symbol, but you need to get used to using symbols with this. And so X bar is what we use for that. And then this is actually the way more of our formulas will look. So we need to get more familiar with this. So you basically add each data value, X1, X2, X3, basically those X and then the subscript say which data value we're talking about, all the way through X sub n, which is our last data value. N is how many data values there are. So we'll use that symbol a lot. N for the sample size. For the data that we're analyzing. And then if we wanted to write that formula in a more condensed format, we can write it with this summation notation. So we have this sigma, which is the sum of, and they've kind of taken part of the summation notation out of it. It really should have, and like I equals 1, and then on top n, so that it like iterates from 1 to n, but they don't write that full in, and this is kind of a shorthand summation notation. But it's the sum of all the data values, each individual x value. I think of it that way, even though the I means maybe something else, but each individual x value summed all up, that's what that is, a bunch of plus signs, and then divided by how many there are. So looking at an example of this, you guys have been doing this for a long time, but here are data on the number of goals scored in 20 games by the 2016 U.S. women's soccer team. So if we wanted to find the mean of that data set, we'd add up all those numbers and divide by 20. And so we'd get an average of 3.15 goals. And so here's what that would look like on a graph. Now, it ends up right here. It doesn't end up actually the mean. It's kind of a measure of center, a measure of what's typical, all right, in an average year, and it does it by that formula. What it gives us actually on a graph is the balancing point. So we see there were these couple of years where it was way up there. It gives us the balancing point if we were kind of trying to balance all those values on a scale or something like that. That's what where that point ends up. So one thing that's interesting to look at is how do outliers affect the mean. So if we took those two high games, those 9 and 10, if we took those out, what happens? And so we calculate that new mean. We see it drops down to 2.44. That's a pretty big drop for just those two. So before we were up here at, what was it, 3.15, and now we're at 2.44. So we've dropped quite a bit. And so what we notice about the mean is it's not very resistant to outliers. A statistical measure is resistant if it isn't sensitive to extreme values. So a resistant measure wouldn't change much if you just add a high outlier, a low outlier, something like that. So that means that the mean is not resistant. It is very sensitive to those changes, so not a resistant measure of center. If we want a more resistant measure of center, and this is a statistic we often use in data sets that are either filled with outliers or heavily skewed, so the mean is also affected by skew. The median is a good choice. So the median is the midpoint of the distribution, so that half the distributions are below it and half the distributions are above it. An important thing to realize is a little detail you may not, or may have forgotten. I know you've done median before, but if the number is odd, it's just the middle number. There's a single number. But if it's even, then there's two numbers in the center. If you have like 16 data values, then you have 8, and an 8. So it's actually the average of those middle two, or the mean of those middle two. You add them up and divide by 2 to get what the median would be. So for example, we've got highway fuel economy ratings for a sample of 25 model year 2018 Toyota 4Runners tested by the EPA. Our raw data is there, and it's 25 of them, so there will be a single number in the middle. But don't just analyze the data as written. Of course, we always, with the median, need to sort it from smallest to biggest. And it's nice to have computers do that for us because that's kind of an annoying process. But here, this middle number will be 22.4. So if there are 25 data values, that means there are 12 to the left and 12 to the right, or greater than it, and that would give us that. So if we go back and do that same thing on the 20 games played by the U.S. women's soccer team, and found their median number of goals scored, sort the data lowest to highest, we have 2 numbers in the middle. So of those 20, we have like the bottom 10 and the top 10. Well, this would be the split right in between, so we average the 2 and the 2. Well, that's just 2, so we're good. But if it weren't different, then you might end up with a number that isn't actually in your data set. It might be something 0.5 or something like that. All right, so comparing the mean and median and how they're affected by the shape of the data. So if we have a roughly symmetric data set here, so we got a roughly symmetric data set, maybe even have an outlier in there, but because the outliers are on both sides and it's symmetric, the mean is not very much changed. So the mean and median are approximately the same. And in this one they look identical, but they won't always be that way. They'll be about the same in a symmetric data set. However, if a data set is skewed, so in this case, this shape is skewed to the left. That's where our long tail is from our center of our data. Here's our center right here on the median or mean. It's skewed left. Well, what happens is the mean is pulled further down by those few low values. The median, all it cares about is the number of values. It doesn't care how far away they are. The mean actually, the quantity itself counts. So a few low values or a low skew will pull the mean more in that direction. And if it's skew right, it'll be the opposite, where the mean is pulled more towards those high outliers, pulled towards that skew. The mean is not resistant to skew or outliers. The median is resistant. If I take this 10 here and I changed it to 1,000, well, if I added up my mean, that would affect my mean a lot, but my median will not change at all. If I change that 10 into 1,000, it will be the exact same. So it is resistant to those. The downside is it maybe doesn't reflect some of that detail that you might want to see in your statistic. So kind of to summarize that, if a distribution of quantitative data is roughly symmetric and has no outliers, the mean and median will be similar. If the distribution is strongly skewed, the mean will be pulled in the direction of the skewness, but the median won't, or maybe if it'll be like, it's still not at the peak. The peak is the most common result. We call the mode. We're not going to actually do much analysis with the mode. The median will be left of, or skewed towards the skew of that, but it's just going to be the center, half the distribution above, half below. For a right skewed distribution, we expect the mean to be greater than the median. For a left skewed distribution, we expect the mean to be less than the median, and the median is resistant to outliers, but the mean is not.